Okay, hi everyone, thanks for coming. I'm going to be talking about A5. I actually have two talks here at FOSS4G. There's an introductory talk and there's the advanced one. So of course I'm doing the advanced one first and the introductory one is going to be tomorrow. So tomorrow's talk is going to be focusing more on what A5 is and what you can do with it. This one is more kind of going deep into the maths underneath that I personally find fascinating, and I hope you guys will too. So first of all, just a show of hands, who actually knows what A5 is? Wow. So that's about a third. Okay, so the other half of you are quite brave. You're going to be flying a little bit blind. Who here knows what H3 is? Okay, cool. So the simplest way of explaining what A5 is basically H3, but with pentagons instead of hexagons. And to explain why you'd want to do this, or in what ways it can be a better use case, then that's going to be tomorrow's talk. But this is going to be talking about some of the maths, which also is going to apply to other systems like H3 or S2. Okay. So first of all, I just want to answer this question of like, why do we want to have these grid systems in the first place? So as you might have noticed, especially if you flew here from Europe, like I did, the world is not flat. If it was, then a lot of things in geospatial would be a lot easier. We wouldn't need projections for a start. And in particular with these grid systems that a lot of us work on, then we could just apply like a two-dimensional tiling. So if you think of like a city and you want to divide it into blocks, then if you think of the city as just like a flat surface, then it's quite easy. But this kind of a tiling pattern breaks down if you try and extend it over a larger and larger area, because the curved surface of the Earth means that you're, in the case of squares, they no longer kind of fit onto the surface. So this is why we need discrete global grid systems. So that's this shorthand here, this DGGS, and H3 is one of the examples, S2 is another one. There's a whole kind of like load of them. I often compare A5 to H3, not because I think it's the best one, but because it's the one that's the most used, at least in industry. But there's actually a bunch of other talks at FOSS4G about grid systems. So Jerome is going to be giving one on Friday, so I'd recommend that. And we have Alexander, who I don't think is here, giving one later today as well. Okay, so if we look inside of a global grid or discrete global grid, then what are the actual kind of very, very fundamental building blocks? And you might see these drawings that I've done here. I've taken these from, I think, a 16th century work by Kepler. So these are things which have fascinated people for centuries and centuries and centuries. Just this idea of like, how can we put together these geometric shapes that either tile or make what are called polyhedrons. So on the geometry side, when we're putting together a grid system, we're going to be looking at polygons, polyhedrons, and projections. And then the other side of a grid system to actually make it useful is a method of indexing, how you can give each one of these cells some kind of like identifier. So quick recap for, I guess everyone knows what a polygon is. Basically, these can be thought of as shapes where every side has got the same length, and in the case of regular polygons, every angle is the same. The 3D extension of this is called a polyhedron, and here each of the faces of these 3D shapes is a regular polygon, and at least this is true of platonic solids. So the first four that we have here, then each of those sides is going to be a regular polygon. The last one is using a rhombus. You can also use this for a grid system, but this is not a platonic solid. Now, another way that you can look at these shapes is using this notation called Schläfli symbols, where in the case of 2D shapes, you represent this as like a curly bracket and the number of sides in it. So this should be fairly simple. And these can go all the way from 3 up into basically infinity. What is interesting about these symbols is that you can extend them to higher dimensions. So when we start talking about polyhedra, then we now need to have like two numbers. So in the case of, probably the easiest one to think about is the cube. We're basically saying here that we are starting with a square, so the number 4. And at each vertex, 3 of these squares are going to meet. And this sort of pattern, this vertex configuration, is going to give us a cube. And in the similar way, you can basically build up all of the platonic solids using basically the numbers 3, 4, and 5. What is neat about the Schläfli symbols is that they don't just describe the like a shape or a polyhedron, but they can also be used to describe tiling patterns, because they're just talking about topology. So they're just talking about how many of a certain type of shape is meeting at each vertex. So some of these I already had on the previous slide. So the first 3. But then the fourth one is interesting, because there we're saying we're going to take a triangle and have 6 of them meet at each vertex. And if you do this, then you can kind of see on the right, you're going to get a tiling pattern, and it's going to extend forever. Like, because these shapes fit together perfectly, then they never kind of wrap around into making a polyhedron. And the same applies for the cube and the chessboard. So that's the 4-3 and the 4-4. And then we have the pentagon one. That's kind of like the odd one out, because that doesn't actually have a tiling. And then finally, 6-3 is the hexagonal version here. And that one is also different, because you don't actually have any polyhedron you can build out of hexagons, which is kind of the reason why H3 has to have pentagons in it to allow it to wrap around the whole sphere. Another way to look at these is in terms of this characteristic called the vertex defect. So this is telling us how much at each vertex we are missing to make like a full angle. So the ones that are tilings, you have a 0 vertex defect because they're flat. And then the bigger the vertex defect, the sharper the vertex you're going to have on the resulting shape. And in the case of these global grid systems, then the sharper this point is, then the more distortion you're going to get when you then stretch it out or project it into a sphere. So here, a low vertex defect is a good characteristic. Okay, so one thing you might have noticed is that on my first slide I had a septagon, octagon, and all of these shapes. Like, why didn't I include them before? And the answer is simple. You just cannot tile with a septagon. It doesn't matter if it's regular or irregular, like they are just never going to fit. And that's because the average angle, which is here, I think 128 degrees, then 3 of those are bigger than 360. There's just no way you can put these together and make a tiling, let alone make a polyhedron. That's unless you live in hyperbolic space, which unless you're like Mr. Pringle, you don't, or if you want to use kind of a concave tiling, but that's cheating, so you're not allowed to do that. Okay, so now we know what these Schläfli symbols do. It's kind of nice to look at their like properties, and you might think like, what's the point? Why don't you just call it triangle, square, hexagon? These guys are actually really interesting because they can go into higher and higher dimensions, where it's pretty hard to imagine what it even means to have like a 4-dimensional cube or the similar equivalent with like a pentagon. But they have a couple of nice properties. So one is, you might have noticed before that with my like list of solids that I have here, there's a nice symmetry. I can always like reverse the 3 and the 4 and get a 4 and a 3. And this is actually encoding a property that polyhedrons have called a duality. So you can see this here where the octahedron, which is the kind of spiky double pyramid, is actually related to the cube, where if you replace each vertex with a face, you get from the from the octahedron to the cube. And in the cube, if you put a point in the middle of the face, then you get back to it. And the same is true of the icosahedron and the dodecahedron. And in terms of this like Schläfli notation, that's the equivalent of just reversing these numbers. Okay, so why am I talking about all of these polyhedra? So it turns out that if you want to make a grid system, you start with these polyhedra which are planar, and you then project them or inflate them, if you want, like this football, into something that's spherical. And the nice thing is that the Schläfli symbols are still valid because they're talking about the topology at each of these vertices. It doesn't matter if your faces are planar or if they're spherical polygons, you still have the same idea. Like on a football, you still have pentagons joining with hexagons. Okay, so with these building blocks, how can we make a grid system, or how can we tile a sphere? Essentially what it comes down to is picking some kind of polyhedron, which I've now described with the Schläfli symbols, and picking some kind of tiling and matching the two using a symmetry. So the first one, that's probably the easiest to visualize, is Google S2, where you're going to start with 4, 3, which if you look up is a cube, and then add on each side this 4, 4 tiling, which is like a checkerboard. And this works because we are matching the symmetry of the tiling, so that's why the 4 is highlighted, with the symmetry of the face of this polyhedron. And the same is true for the other one. So Uber H3 starts with 3, 5, which is an icosahedron. And the only tiling we can use, we can't use, for example, the one with squares. We have to use one that has a 3 in it. So here we're using the hexagonal tiling. And the nice thing here is that the 3 is not coming from the hexagon itself, it's coming from the symmetry of how many hexagons we have around one point. Okay, so once you've managed to tile the shape in this way, the last thing that remains is an unprojection from one of these faces to the sphere. And here it's basically like you can choose whatever projection that you want to have. Like different types of projections are going to give you different properties. But the important thing, and this for me was the kind of, maybe not aha moment, but like an interesting observation, is that when you do this projection, then regular polygons that you started with get warped, they get squashed. And you can see this on the S2 image here, that these cells no longer look like the squares they started out being. So even though you start with regular polygons, you actually end up with irregular polygons on the sphere. There's just no getting around that. Okay, so there was one tiling missing here. There was no way that we could start with this 5-3 dodecahedron and do a tiling on it. And the answer is there is no kind of Schläfli symbol that has a 5 in it that is a tiling. We don't actually have anything that we can cover our dodecahedron face with. Or do we? So this is kind of how I started with A5. I came across a paper on pentagonal tilings from the 80s. Honestly, I don't know how, but I just got linked to it somehow. And in that I discovered, or I found these like 3 pentagonal tilings, which are nice because, especially the last one, is it's built from irregular pentagons, but when you put them together, they form a regular pentagon. So this is now a tiling that you can use on the side of a dodecahedron to cover that face. Now, it doesn't have a Schläfli symbol because it's not a regular polygon, but it does still work. And if you get multiple of these faces together, then even though the edges are jagged, then you can actually join them together on the sphere, and they perfectly mesh, and you end up covering the whole world. And that, in a nutshell, from the sort of mathematical perspective, is what the whole A5 tiling scheme is. So in order to actually tile this polyhedron, this dodecahedron, you have to relax the requirements that have been used in most of the other systems before. And rather than using regular polygons, you have to use irregular ones. The aperture of the system is 4, which means that you can keep subdividing and having more and more cells covering the kind of the sphere. So you can see that on the animation on the right. And every time you do that, you get 4 times as many cells. So this is the same as subdividing like a chessboard, or in S2, this is how it works. By contrast, then H3 is different because when you subdivide a hexagon, then you're going to get 7 more. I mean, that's one way you can subdivide it. A quick note on projections, because I think I'm going a bit slow. One part that I kind of skimmed over before is that when you're going from the polyhedron to the spherical polyhedron, you have to kind of map a flat surface to a curved surface. And you do that using a projection. So the projection that's chosen in A5 means that it exactly preserves area. And then as a result, the area variation on the sphere is non-existent. Compared to something like H3, where you can see that the area variation is much bigger. The name of this projection, it doesn't actually have a name, or not a well-agreed name. There is a nice paper from the 90s about projecting on these kind of polyhedral globes. A common projection is one called ICEA, which stands for icosahedral Snyder equal area, and this uses the icosahedron. But because in A5 I'm using the dodecahedron, then I think the kind of most natural way to refer to it is DCEA. But these two projections are actually kind of quite simple, but this would probably be a topic for another talk. Maybe me and Jerome will do that someday in the future. Okay, so if you followed everything that I said now, then you kind of have all the knowledge that you need to build kind of a visualization with A5. You know how to segment the world into equal area cells that have got a single topology. And that means that you can do visualizations like this. You can get points, you can bin them into cells, and using this you can basically represent data that has some kind of spatial distribution. The part that is missing is a way of actually referring to each of these cells, and that's kind of like the secondary part of grid systems, which you need to make them useful, because you kind of want to represent this data not just in like an image format, but you might want to store it in a database, and each of these cells needs to have an identifier. So what you need is an index. So indexing in these grid systems comes down to this problem of how do we represent something that's two-dimensional, so that's the surface of the sphere, in a one-dimensional manner, which might just be like a single identifier in a database, or just a number. And it turns out that the elegant way of doing this is thinking of the problem of like giving an index to each cell as a way of joining the cells with a curve that passes through every cell around the whole world. And then you can basically think of this as a way of reducing the 2D problem to a 1D problem. So then you just sort of say, okay, I have a curve, and cell number 0 is the one at the beginning of the curve. Cell number 2 is, cell number 1, if you're starting with 0 indexing, is the second one, and so on. And the trick is to design this curve in such a way so it kind of has good spatial locality, so that the data that you're storing in your database is kind of nearby on disk for points that are nearby in the real-world space. So I think I'll just quickly switch to the A5 website to like demo this a bit, because I was too lazy to make a video, and it's nicer to show it here. So the way this curve works is, rather than being just one curve for the whole world, then it uses one of these triangular patches, which is a fifth of a pentagon. And you can, in this visualization, kind of explore how it's sort of linking these different cells. And as I make the resolution of this curve bigger, then you'll kind of understand why it's called a space-filling curve, because it kind of looks like this is a solid object. Now, once you have one of these curves, then you can join 5 of them together to form a sort of a pentagonal patch, and then you can take 12 of these and arrange them in such a way so they cover the whole world. And this slider here I can kind of use to show like a subsection, and this is kind of what I was talking about, it having a nice spatial locality, that half of the curve is kind of covering half of the world, but in like a nice pattern. One final thing that's quite interesting about the arrangement of the curve that A5 is using is that it starts on the North Pole, and then it passes through 8 pentagons, which represent the majority of the landmass on the Earth. And the last 4 pentagons are mostly the Pacific Ocean. Like, we in New Zealand still make it into the first 8. And this is useful because it essentially makes it possible to go and this might be clearer with the next example, you can go to a more higher resolution level for these first 8 pentagons than the last 4. Okay, so we have our curve. The question is, how can this then be indexed in some way that is kind of useful? How can it be serialized? And here the trick that you're trying to do is work with the minimum kind of storage space that you have available to you, because the more kind of wasteful you are with the way you represent this index, the fewer resolution levels you can have. So a good comparison here is that H3, then the way they've designed their indexing, then the smallest hexagon you can have is about 1 meter in size. With A5, the smallest pentagon you can have is 30 millimeters, so it's something like this. So like a couple of orders of magnitude smaller. And in part, the reason for this is just like a bunch of decisions of how this has kind of been represented. So the way you kind of construct one of these indices is, it's kind of easier to think of this as like an expanded 64-bit number. So that's this value that I have here. The first 6 bits are representing which of the quintants, I call them. So each of the dodecahedron faces is split into 5, which gives you 12 times 5, so 60 of these. So those first bits just tell you which of those kind of cells that you're in. And then in each one of those quintants, we have the cell, the space filling curve that I showed you earlier. And it's just simply a value along that curve. And then, depending on which resolution level you're in, you need more or less space to store this curve. So the first level is only going to have maybe 4 steps on it. The next one will have 16 and then 64. So that's what this like pink index here is showing. So the location of these, the first 0 and 1 from the right, tell you the resolution of the index, and then all of the bits that are in between there tell you the position on the curve. And the nice thing about doing it in this way, even though this all seems kind of very abstract, is that if you then play around with this, and if I kind of zoom in and out on London, then you're going to notice that basically all of the bits are staying the same. It's just that the marker bit, the sort of pink bits, are moving a bit to the side. So you have an interesting kind of like spatial relationship between the different indices in the system. And if you want to get the children of this cell here, then it basically comes down to just moving the pink bits to the right, jump, and then adding either 1, 1 or 1, 0 or 0, 0, depending on which of the indices, which of the children you have there. Okay, I think that's everything I have. Yeah, and I'm just about on time. Maybe we have time for one question?
Thank you, Felix.
Oh, and one last thing. I have t-shirts, so if anyone feels like they want to look as cool as me, then yeah, come and talk to me afterwards. So.
All right, let's get some question on the floor.
Hey, thanks for the presentation. It was very cool. And when I'm thinking about these kind of grids and H3 being a hexagon, it seems to me like it looks kind of like a circle, a bit like a circle. And I can't easily get over the fact that the pentagons like aren't as looking like a circle as the hexagons. So is that actually an issue, or is that just all in my head?
So it is an issue. The hexagon in this way is the most circular or compact shape. So there is a measure of this called IPQ compactness. And the hexagon does the best here, but it's almost like the more size you have, the more compact you are. So the pentagon does like pretty well. So it depends on if you're talking about this for analysis or visualization. Like if for visualization you want it to look like a hexagon, then I guess you need to draw it as a hexagon. But if you're talking about aggregating data, then it's not that far behind the hexagon. And also bear in mind that even though the hexagons look like circles, then they're actually getting squashed even in H3. They're not actually exact in terms of, they're only exact on the face of the icosahedron before they're projected.
Yeah, that was a really good presentation. Thanks for that. You'll probably dive into this tomorrow, but what's your use case, your like perfect data set that you would want to play with H5 with, or A5 with?
I would really say come to the talk tomorrow because I have a whole section on that. Yeah.
Okay, let's get one more here and then.
Yeah, that was related to my question, like why another grid system, say, like what? So that's the use case of A5.
So I think the biggest difference compared to the ones that are in use now, not existing, is that none of them are equal area. And I'm going to try and explain tomorrow with a case study why this doesn't just give you like a biased result, but can actually give you an incorrect result, and try and persuade you, because it's not the first, you're not the first people to ask the question. In fact, there's 2 of you in one room already. So yeah.
Okay, thank you. Let's thank again Felix for now and